From Utah Public Radio, this is UnDisciplined. I'm Matthew LaPlante. A few months ago, I was hiking in Nevada's Ruby Mountains. And the foothills were shrubby and dry and desertous, and the dirt was craggly and brittle. But as I ascended, I found myself in lush aspen groves and dense coniferous forests, trotting through creek beds and marshes. And if you've ever hiked from the foothills to the top of the mountain, you understand that elevation plays a huge role in the biomes that you encounter along the way, with plants and animals and weather patterns and even the availability of oxygen shifting as you ascend and descend. But because a lot of these sorts of areas are hard to access, they aren't well represented in long-term observational data sets. And climate scientists aren't yet able to adequately model what has happened and what will continue to happen to these places under continued climate warming. But these are very clearly very important areas for water, for biodiversity, for our enjoyment of the natural world. These are also potentially vital areas for carbon storage. We often think of carbon dioxide as something that dissipates evenly across the globe, but the reality is that free carbon in our atmosphere is not evenly distributed. It's patchy, with high concentrations in some places and lower concentration in other places, and these patches are dictated by large and small-scale atmospheric circulations. And that's a big part of the reason why the Ameriflex network was launched in the 1990s, to quantify the magnitude of carbon sources and sinks for a range of terrestrial ecosystem in the Americas and how they might be influenced by environmental disturbances, land management decisions, atmospheric pollutants, and climate change. One of the ongoing Ameriflex-sponsored projects is the New Mexico Elevation Gradient Project, a network of 9 observational towers distributed across 5,000 feet in elevation that have been operational since 2007. Marcy Litvak is the principal investigator for that project. She's also a professor in the Department of Biology at the University of New Mexico and the co-director of the university's Arid Center, which is focused on identifying ways to create resilience against climate change. Marcy Litvak, welcome.
Thank you.
Marcy, New Mexico is among the most sparsely populated states in the country. There are about 18 people per square mile here. I think that a lot of people might have a hard time visualizing what this state looks like if they don't live here. But the topographical and biological diversity here is pretty breathtaking. Can you talk a little bit about that?
I loved the way that you described, your hikes in Nevada, and that's the way I love to think about New Mexico too. Is if you start down kind of in our desert ecosystems and you hike uphill, you'll hit so many different types of ecosystems and biomes in a really short period of time. It's as you go up, climate changes, and that basically is driving all of the changes we see in the plant community as well.
When people you meet, you're at a conference, you're traveling somewhere, and you're just I'm from New Mexico, and they're like, oh, you live in the desert. And you're like, it's so much more than that, right?
I mean, I do feel like you're right. That's probably the first thing that comes to mind is it's just a desert. But, you look out the window here, right? It's anything but just brown. There's a lot of vegetation that's growing here. It's maybe not as big or as diverse as what you find on the East Coast, but we can hold our own.
Among all of the different and various biomes here, do you have a favorite place? What's the place that speaks to your heart when you're there?
Oh, that's so interesting. I talk about that with my students all the time because we have, our sites are distributed along this big elevation gradient, and it really changes based on time of year. I personally am not a fan of the lower elevation sites in the summer, but they are absolutely stunning in the winter when the light is just right. I mean, I think if I had to pick one I like the most, it's probably our Ponderosa Pine woodland site. It's just gorgeous. It's kind of a good mix of enough shade and beautiful canopy and interesting things going on.
And because you're the director of this elevation gradient project, you get to see all of these all the time, right? You do a lot of field work.
I do. Yeah, I don't go in the field as much as I would like to anymore, but I do. I get to all of the sites at least once a year. But we're adding new components to these sites all the time. So, for example, just this past year, we started a new study that's funded by DOE. And we started at all of our sites where we've been measuring ecosystem scale fluxes for going on 18 years. We now started instrumenting the roots so that we can look and see hydraulic redistribution, which is the ability of plants to passively redistribute water between roots and the soil. We've added that component to all of our sites, and there's just so many new components that we can keep adding to it that it keeps it really exciting.
Okay, I want to go into that. Like, how do you do that? How do you instrument the roots? Because I can kind of like visualize, and I've seen your towers. I've seen pictures of your towers. Like, I can visualize how they're monitoring carbon dioxide and other things. But how do you? Presumably, you're drilling something into the ground.
You don't have to drill into the ground, but you do have to get inside the root. So are you familiar with sap flow probes? So you can install probes on boles of trees, like on the main stem of trees, and you can measure the rate at which transpiration occurs. And you can do that in roots too. It's the same thing. So you just have to excavate the roots from the soil, pop this sensor in. And the cool thing is not only can you measure, like how fast sap is moving through, but you can see what direction it's moving. So you can tell if it's moving, going down, water's being moved deeper into the soil layers, or being moved up through to the canopy.
Probably when you first heard of this, you were like, okay, yeah, that would be some data. And then I imagine that you started thinking about like all the ways you could use that data. And now there's too much of it and you'll never get through all of it. Am I right?
That is exactly what is going on. Because that's the cool part, is that what these towers measure is like what's going on at the ecosystem scale. But in order to really interpret that, we need to instrument each different individual species and see what they're doing. And then when you think about what's going on in individual plants, you think about above and below ground stuff, and then you think about what's going on in the soils, and the whole ecosystem is made up of so many different components that it gets a little dizzying, and you have the desire to want to monitor every little component, and then we end up in the situation you just described.
And that's, like, in addition to being like a data problem, that's also an engineering problem, because you have to have all of these different pieces of equipment. They have to be maintained. They have to be functional. They can't stop working because you stop getting your data.
Exactly. Right. And then you want long-term data, right? Because the longer period over which you're able to collect these data tells you so much more about it.
So these 9 towers that you've been maintaining since 2007 is kind of, like you said, it's kind of dynamic. They are changing over time. You're adding instrumentation over time. But do you add the same instrumentation every time to all 9 towers? Or, for instance, the one that's up in the junipers, does it have different instrumentation than the one that's down in the shrublands?
Yeah, that's a really good question. We do try to maintain consistency over the whole gradient, but occasionally, so for example, one of the things that we're adding right now, we only have it in one site, our thermal cameras, so that we can measure infrared imagery from the canopy, and we can use that to determine, if some species of plants are taking up water more than others and at what time, and relate that to our soil water content measurements and all those things. So that's something we occasionally will bring in one site, and then we go get a grant to be able to install it over the entire gradient. But for the most part, we try to keep things as consistent as possible.
So let's talk about the thing that was being measured, is continuing to be measured. That was sort of like the start of all of this. Because carbon dioxide is invisible, we often don't think about the ways in which it gathers and it dissipates, and in which it affects and is affected by different topographies and different biomes. When did that thought start to occur to you, that we weren't just like being blanketed with this even blanket of carbon dioxide everywhere, that it was different everywhere, and it was different everywhere in part because of what was already there?
I think actually I went and did a postdoc with Michael Golden at UC Irvine. And in Canada, this is probably where these ideas really kind of started to gel, because what we were looking at in the boreal forest was the impact of fire, and how forests in different successional stages were taking up different amounts of carbon. And so that's what I did in between my PhD and when I started here in New Mexico. And so I think, it just seemed like a natural thing to carry that idea forward to understand what the spatial heterogeneity was doing in terms of CO2 and water flux.
When you see the way that fire moves through an ecosystem, it becomes very, very clear that even within a very small area on a map, but that incorporate a large expanse of different topography and different plant and animal life, and like maybe there's a stream running through here, or maybe there's an outcropping of a certain kind of plant here, and that changes everything in this short amount of space that, if only represented by a pixel of 1 kilometer by 1 kilometer, really misses a lot of that nuance.
Absolutely. And the cool thing is to think about, how that diversity over space gets represented, but also over time. So a fire comes through, completely wipes out that forest, and then it grows back. And as it grows back, everything changes constantly, right? The plants, the order of the plants that they come in, and the density of the plants, the types of plants that are there, all of that has an effect. And so really trying to capture that and explain it. A lot of the things that I love looking at now are concepts that were well known by ecosystem ecologists and put out in textbooks for, many, many, many years, but there were never numbers on the axes, right? Because you couldn't go in and measure these things. And I think that's what tools like eddy covariance really provide for us, is a way to actually quantify how much carbon is being taken up in any ecosystem at any time.
Okay, let's talk about how we get those numbers for data for eddy covariance, right? How do you get from this idea that, okay, these areas are different, they're very different from place to place. How do you get from there to, I'm going to figure out a way to help build 9 monitoring towers across New Mexico so that I can measure the covariance of everything?
Yeah, that's a really good question. I mean, I was really fortunate. And when I started at UNM, 4 of these towers were already up and running. So 2 of them were at the Savietta LTR site. There was a project that was started many years ago by Eric Small to ground validate remote sensing products. And that was in a desert grassland in the creosote shrubland. About the same time, there were 2 towers that were installed in the Valles Caldera, which represent our high elevation end of the gradient. Those were installed by folks from University of Arizona through a science and technology project through NSF. And so when I started, these were kind of thrown in my lap because I knew how to run towers and nobody else was here to do them. And so what I decided to do was to try to capture the middle part of that gradient to, then better put together an elevation gradient, because we had the low elevation sites, we had the high elevation sites, and I wanted to know also what was going on in juniper savanna and pinyon juniper woodland. And then since then, the gradient has grown mainly based on disturbance gradients. So we received some funds from Department of Energy to look and see, we had all this pinyon mortality throughout the entire Southwest, starting at the turn of the century, and we were really interested in what impact did that have on how much carbon and water and energy was exchanged with the atmosphere.
What was happening to the pinyon?
The climate changed significantly about at the turn of the century, and we moved into a drier part of the climate, and that's where we started to see these super extreme droughts start in this region. And pinyon in particular were really, really vulnerable to this change in incoming precipitation. They were physiologically really stressed, and then pinyon bark beetles came in at the same time, and it really just
It was like
decimated.
a 1-2 punch.
Exactly, all over the Southwest. And so what was really interesting about that disturbance is it's different from a fire, right? Fires come in and pretty much take out everything. Here we just had mortality of one of the dominant species. And so that's something that I was really interested in, is what if because the juniper were fine, the juniper didn't seem to be affected, and most of the pinyon died out. And how does that impact the way that the ecosystem functions?
What did you find when this really important member of the ecological community disappears? What happened with the rest of the community?
One of the things that was so interesting, so we went in and we mimicked that mortality by girdling a lot of pinyon in one area where we had an eddy covariance tower. So we took out all of the adult pinyon. essentially. We girdled them, so we left them standing, but we severed the phloem. So they were no longer able to function. And what was really interesting is right after we did that, there was a drought. And what we found was, and we had paired sites, one where the pinion was left alone and one where we removed the pinion. The ecosystem got hotter and drier in the site where we removed the pinion. And what I think was going on is the pinion were playing an important role in reducing radiation hitting the ground. And so when you take out the pinion, that increased evaporation rates. We saw soil temperatures get higher. We saw soil water contents decrease, and the remaining juniper did worse.
And you can monitor all of these things because you have those towers there that are monitoring so many different variables over time. You can see that, and you can do experiments like this and get good long-term data on what happens over time in ways you really couldn't if you didn't have that stable tower there.
That's exactly right. I mean, you can go in and do manipulations on smaller scales, and we do those all the time, on really small plot scales. And then you have to scale that up to the ecosystem. Or you can do these large scale manipulations, and they're hard to do on that. I mean, it was a 4-hectare area where we had to remove the pinion.
How many people did you have doing that?
We were able to use off-duty firemen who had chainsaws, and they came in and did the work for us beautifully.
So pretty early on to the use of these monitoring stations, you and your collaborators pointed out that changes in temperature and moisture have really profound effects on how plants inhale and exhale. And the implication is that as these meteorological variables shift under climate change, or shift perhaps in response to something like losing pinion, which is a response to climate change, that the carbon balance is going to shift too.
Absolutely. Yeah. I mean, as soon as one of the things I'm really interested in is the relationship between structure and function in these ecosystems. And so anything that you do to change the structure is going to result in a change in the function. What's really interesting is about when you do change like water availability, right? That's been changing over time and how these ecosystems respond to it. And that has, unless you're talking about this large scale mortality event like we see with pinion or like a fire moving through, what's really interesting is to kind of try to capture these more nuanced effects. So with an 18-year time series, you can start to do that, right? Like with 18 years, we have a whole range of soil water availability, and we can directly measure how carbon uptake or how carbon release responds to those changes in soil water availability at different layers in the soil, deep soil versus shallow soil. And one of the things that's been really interesting to us is to compare, are the higher elevation sites more sensitive to those changes in water availability or the low elevation sites? So kind of get a handle on the relative sensitivity of all these different ecosystems to the changes in climate that we're seeing.
Because these shifts are going to be different at, say, 5,000 feet versus 7,500 feet versus 10,000 feet.
Exactly. And these plants have evolved in these ecosystems, and they have mechanisms to deal with these changes based on the amount of water that they've had available to them and how variable these parameters have been over time. They have different ways of doing that.
And that all affects the eventual mix of biodiversity that we get on the other side of whatever the disturbance or change is.
Exactly. Yeah. That's one of the really interesting things is to try to use these data sets to think about like, what are our landscapes going to look like in the future? So if we see over the last 20 years how each of these ecosystems are responding to changes in soil water content, and we know what's coming ahead, we can make some predictions to see which plants are likely to survive and why.
This is so interesting, though, because it sort of brings together two ideas that we've been talking about today. One is that we can use this data to make predictions about what's going to happen. But two is that it's so dynamic and it's so complex that it's also really hard to, like, even if you have this really great data from this one tower site, that tower is set up in a place that's, 150 meters different than a completely different area at a slightly different elevation or a slightly different gradient right. And so, I mean, that's got to boggle your mind sometimes thinking like, okay, well, I'm going to make this prediction, or I'm trying to use this data to make a prediction about what's going to happen, but also, meh.
Absolutely. I mean, even when we were setting up our two sites where we planned to girdle one pin, like girdle all the pinion in one and leave one intact, they were 3 kilometers apart from each other in the same area. And we were amazed at how, like when we were running the towers together, there were differences. We see the same thing at the Sevietta. We had 2 grasslands that were set up across the road from each other. They look identical when you're looking at them from above, and they are completely different.
So some people might look at all of this and say, well, look, there's just too much chaos in the system. There's too many moving parts that affect other moving parts for any of this data to ever be useful for understanding what's happening and why and how it's going to continue to happen in the years and decades to come. But I don't gather from our conversation that you feel that way. Like, even knowing this complexity, even being immersed in these huge data sets, you believe very strongly that this data becomes very useful to us moving forward.
Absolutely. Like we have to have the direct observations to use them in 2 ways, right? To use them to help parameterize these models and provide kind of the baseline, but also to validate them. Without having these observations, we don't have any of that. So, I mean, one example is immediately when you talk about how complex these ecosystems are, one of the things that I think about is how complex the responses in all of these ecosystems are to rainfall pulses. I mean, you would think it might be kind of a simple thing, right? We have some really simple theoretical predictions of how ecosystems should respond. And I started looking at this right when I first got here to UNM and started making these measurements, and it was so complex. There's so many different factors. I can't say that we've solved the problem. We haven't at all, but because we have 18 years of responses to precipitation pulses, we have enough data now where we can start to explain the responses and the important factors that are changing them.
You mentioned earlier your favorite place among all of these. What's likely to come for that place under, let's say, like a moderate climate warming scenario, 20 or 30 or 40 or 50 years?
One of the things that I think is interesting about the Ponderosa Pine site is it does appear to be incredibly resilient to the changes that we've been seeing in climate. It's really sensitive. You know, most years it's still taking up carbon, but it's really variable. And for example, when you compare it to our high elevation site where we have a lot of white fir and Engelmann spruce, Doug fir, that site, it appears over the last decade to show a decrease in the amount of carbon that it can take up. It has responded in a really sensitive way to the decrease in water availability, and it hasn't bounced back to what we were seeing before the climate started to change, where Ponderosa pine has. I mean, these ecosystems are taking up quite a bit of carbon. It might not be as much as we see in mesic ecosystems, but if you were to look across the 18 years that we've been making our measurements, they are almost continuously taking up carbon, such that at the end of 18 years, it's a really impressive amount. And I feel like the thing about these ecosystems that's so important is that maybe they're taking up less per square meter than more mesic ecosystems, but when you take the spatial extent into account, it becomes really, really important in terms of being able to quantify that.
And so having them continue to be healthy and continue to function the way they've been functioning is important for maintaining the balance of carbon circulating in our atmosphere.
Absolutely, because even if there's a small change because of the spatial area, the extent that they occupy, that can make a big difference.
That's Marcy Litvak. She's a professor of biography at the University of New Mexico and the principal investigator for the New Mexico Elevation Gradient Project, a network of 9 observation towers distributed across 5,000 feet in elevation that have been operational since 2007. She's also the co-director of the university's Arid Center, which is focused on identifying ways to create resilience against climate change. Marcy Litvak, thank you.
Thank you very much.
UnDisciplined is a production of Utah Public Radio, and if you happen to live in Utah, you can listen to us on UPR every Thursday morning at 10:30. If you miss us, then you can listen to every episode of UnDisciplined wherever you get your podcasts. Our program is supported by the College of Humanities and Social Sciences at Utah State University, and of course from listeners like you. You can support our work at donate.nprstations.org/UPR. Our producer is Reagan Edelman. Our theme music is Little Idea by Benjamin Tissot, and I'm Matthew LaPlante. Thanks for listening. Now go have big ideas.